What's up guys? Welcome back to today's video and I'm here with you all to discuss one another simple topic from the chapter chemical bonding. And the topic that I have chosen for today is Vsepr. Some teachers and some students call it as Vsepr theory because like we are so pro in speaking Vsepr. Some people call it as Vsepr theory. It's up to you, whichever way you want to pronounce it, you can call it that way. Okay. By the way, what is Vsepr theory? It stands for valence shell electron pair repulsion theory. Oh my God, such a long name for the theory, Vsepr, valence shell electron pair repulsion theory. Okay, question number one, why do we need to study this theory? What is it all about? You remember when we were doing Lewis dot structures, I said that Lewis was not able to explain the shapes of molecule. I remember drawing carbon dioxide or water, and I said that we draw carbon dioxide like this and we do not draw carbon dioxide like this, because Lewis couldn't tell us what is the shape of the molecule, right? But this theory, which is valence shell electron pair repulsion theory, is very, very important because it can easily predict what will be the shape of any given molecule. Okay, so the name itself will be telling you what the theory is all about. Okay, let us start with the name. It says valence shell electron pair. So this is one thing. You know, if an atom is there and it has to form a bond. So atom is made up of, I told you, nucleus plus so many shells will be there, right? And let us say all these shells are filled shell and this is the last shell. And since this is the last shell, we call it as valence shell. Am I right? Now we studied this at the time of Lewis also, that when the atom is going to form a bond to any other atom, it is not going to use all the inner lying electrons. So the electrons which are lying closer to the nucleus will not be used in participating for the bond formation. Reason being, since these are inner lying electrons, these are deeply seated electrons, they are more towards nucleus, they are more held together by the nucleus, so they are not free for bonding. And since they are not free for bonding, the atom will not use them for the bond formation, right? So this theory says that if the atom has to undergo bond formation, it will be using only the valence shell electrons. Okay, so these are the first two words of this particular theory. Then it says that, let me just draw, let us take the example of water molecule. Now if I talk about oxygen, you know that oxygen has 2, 6, so there are 6 valence electrons. Okay. Now if oxygen has to form a bond, let's say we are talking about oxygen forming a bond with hydrogen, it says that the valence shell electron pairs, VSEP, valence shell electron pairs, are of two types. Either these are ones which are known as lone pair of electrons, or these are ones which are known as bond pair of electrons. I told you while doing the Lewis dot theory also that these two electrons which are not taking part in bond formation will be said to be the lone pair of electrons. And the ones which have taken part in the bond formation, these electrons are said to be the bond pair of electrons. Okay, so this is what is told to us by valence shell electron pair repulsion theory, that the atom takes only the valence shell electron pairs to take part in bond formation. Those valence shell electron pairs are further of two types. One is bonding electron pairs and the other are non-bonding electron pairs. Okay, now the theory says that the bond pair of electrons are like more, I should say they are kind of more rigid, or they are more localized, whereas the lone pair of electrons are kind of delocalized. Now what do we mean by localized and delocalized? Again, I will first give you one simple example and then we'll try to understand what are localized or delocalized pair of electrons. Okay, so this is mere ghar ki baat. This is what happens at my home. Suppose this is me, okay, and I'm cute. Let me draw myself very cute. Okay, so this is me and this is my dad and this is my mom. Fine. अब होता क्या है हमारे घर पे? When both my mom and my dad are there together with me. तो अगर I say to my dad कि पापा प्लीज़ आज पिज़्ज़ा ऑर्डर कर दो, बहुत तेज़ भूख लगी है, तो my mama, she hears all these things from the kitchen and she starts shouting. अरे ऐसे कैसे पिज़्ज़ा ऑर्डर कर दो, इतना सारा खाना बनाया, आज पिज़्ज़ा ऑर्डर कर दो, blah 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 blah, and she starts telling all these things like anything. And finally what happens? I'm like, this good smiley face of mine is like, oh my god, aaj bhi pizza nahi mila. This is what happens when both my mom and dad are there at my home together. Ab I'll tell you one another situation what happens. Let's say my mom was there and someone called my mom and said, yeah, let us go to market. So she said, okay, you two manage. This is me, okay? I'm smart. So she said, I'm going to market. Now both of you manage. And you know, then I don't say anything. My papa himself will say, yaar pizza khana hai, aaj pizza order kar de. And I enjoy like anything. I mean, this is like wow situation, right? I'm sure this must have happened in your home also, right? So this is what is said to be localized and delocalized. Now try to correlate. When I was under the influence of both my parents, when my mom and dad both were there having influence on me, I was kind of localized. I used to say, or I simply say what they want me to say. I'm kind of quiet person, right? So I'm kind of localized. But let us take the other situation. When my mom is not there, she went to market or somewhere and my dad is there. I'm like, yeah, full on masti, full music, full pizza, blah, blah, blah. So I'm more delocalized, right? I'm more free. So now let us talk about the same thing in case of atoms. I am talking about water molecule. These two are lone pair of electrons and these two are bond pair of electrons. These two are also bond pair of electrons. Okay. Now don't you think in this situation these two bond pair of electrons are under the influence of two parent atom. One is oxygen, one is hydrogen, and both of them are holding the two electrons very tightly. Okay, so these two electrons are said to be localized electrons. Fine, they will not move in a wide area. They'll be there in that congested area. But if you see at this lone pair or this pair of electron, so this pair of electron is only and only under the influence of one parent atom, which is oxygen. So his father, let's say hydrogen, or his mother, let's say hydrogen, went somewhere to market, and this is the same situation where the pair of electron is under the influence of just one parent atom. Now since this is like more free because only one oxygen is having a hold, not the other atom, so they try to expand. They take more area, they occupy more volume. Okay, and that is the reason we call them as delocalized electrons. Okay, so which have occupied a larger volume. That is what is said to be delocalized electrons. Fine. Now one thing I want to clarify here, in NCERT it is given that the lone pair repulsion is greater than lone pair bond pair repulsion greater than bond pair repulsion. I have seen students mugging it up, I have seen teachers saying that just mug it up, this is the only important thing you have to remember. But I would like you to stop here for a minute and think why these two should repel each other. You know, right, the bond doesn't mean, let me remove this and let me draw it again. The bond doesn't mean that there is a line and there are two dots in between, right? No. So the electrons or the bond is simply the electron cloud because of 2 electrons which is there in between oxygen and hydrogen, right? Similarly, this electron is nothing electron, but it is an electron cloud which is there between oxygen and hydrogen. And these 2 electron clouds are kind of loosely held. Okay, now these 2 electron clouds, they are like they are spreaded so widely that they repel each other, and hence I call it as the repulsion between lone pair and lone pair. And since both the lone pairs are like occupying very large volumes, so they'll repel each other to the maximum. Whereas these 2, which is bond pair, I told you, right, that they are already in a congested space, so the repulsions are also less. So these also repel each other, but not as much as lone pair. And if I talk between these 2 or between these 2, this is lone pair, bond pair repulsion. So lone pair repels more, bond pair repels less. So the statement that we got is lone pair repulsion is greater than lone pair, bond pair repulsion, which is greater than bond pair repulsion. Okay, so this is what is explained by the Vsepr theory, that the repulsions between lone pair will be maximum. Okay, now let me write the name of Vsepr again. So this says that valence shell electron pair repulsion theory. They have specially mentioned this R stands for repulsion. So according to Vsepr theory, it says that when hydrogen and oxygen, they try to come close to each other, oxygen has got 2 types of electron pairs, bond pairs and lone pairs, right? Now they will try to come close to each other, but they can come close up to a maximum length only. If they will come more close to each other, let us say this is the structure. If these 2 electron pairs will come more close to each other, there will be repulsions. So they want to be maximum away from each other, and the distance should be such that there has to be a minimum repulsion. Okay, so the lone pair want to orient themselves in such a way that they are maximum far away from each other and they have minimum repulsions. Okay, so these were all the postulates that are covered in Vsepr theory. Now, if I go like a traditional teacher, there are 2-3 tables which are given in NCERT, and your teachers will ask you to just go through the table, remember the structure, and that's it. Okay, I am not going to do that because that's kind of mugging up thing which I don't want. So now I am telling you one formula which is like so damn easy that if you know the formula, you will be able to predict the shape of almost any molecule you feel like. Fine. So let us start working with the formula. The formula says steric number. So this is not serial number 1, 2, 3, 4. This is steric number. So this is half number of valence electrons of central atom plus number of atoms attached by single bond plus minus charge. Now what is this formula all about? Wait for a minute, I'll tell you all the things one by one. There are 2-3 things that you have to remember. Suppose there is a molecule CO3 2 minus and there is a molecule NH4 plus. So you have to find out what is the shape of these 2 molecules, let's say. Now here the charge is 2 minus, right? Okay, and if I'm saying plus minus charge, so when this 2 minus is there and when you write this in formula, you will do it as plus 2. And here if plus 1 is there, when you mention this in formula, you will be doing minus 1. So plus becomes minus, minus becomes plus. This is rule number 1 you have to remember. Rule number 2 you have to remember, let's say we are talking about CO2, we are talking about H2O, we are talking about CO3 2 minus, we are talking about SO2, blah 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 blah. We can be talking about any of the molecules. You always have to assume that if oxygen is there, it will be forming a double bond. Okay, whether it forms a double bond finally or it forms a single bond, I am not talking about what happens finally. I am just saying I have written the number of atoms attached by single bond. How many atoms are there which are attached by single bond? If you are talking about oxygen, just remember oxygen attaches by a double bond, double bond, double bond, never ever by a single bond. Okay, now with these two things in your mind, let me start doing different questions and let me show you how good this formula, how helpful this formula is. Let us start with the molecule BeH2. Fine, this is the first molecule I am starting. So first we'll try to learn how to use this formula, and next video I will be taking maybe 40 or 50 examples and I'll solve all of them in like fraction of minutes. Okay, so see here, BeH2, first write beryllium, electronic configuration 2,2. So half number of valence electrons of central atom. By the way, what do we mean by central atom? Central atom is generally the one which is, point number 1, bigger in size. The one which is bigger atom will be central atom. Like for example, there is an elephant. I can make 2 or 3 mouse sit on that elephant, right? But I cannot take one mouse and make 2, 3 elephants sit on him. Obviously, right? So the elephant will be the central atom. And another thing is the less electronegative atom. In case the size is almost same, so we will choose the less electronegative atom as a central atom. If not this, we can also say that the one which is only one alone will be the central atom. Like BeH2, 2 hydrogens are there, but beryllium is 1. So that way also I can say beryllium is a central atom. Okay, and all others will be known as side atoms. The ones which are attached to something will be known as side atoms. Now let's start doing this question. We have half number of valence electrons of central atom. So beryllium is our central atom, valence electron is 2. Plus number of atoms attached by single bond. Look here, there are 2 hydrogens and we know that hydrogen gets attached by single bond. So I'll do plus 2 here. Is there a charge on the molecule? No. So plus minus 0, I am not writing. Overall answer comes out to be 2. If the overall answer comes out to be 2, the shape will be, the hybridization will be sp. Now you might be thinking, what is hybridization? Wait for a few more lectures where I'll tell you what is hybridization. You have to re-watch this video after hybridization. Right now this is not important for you. So hybridization is sp and the shape will be BeHH. See, can we say that if you take a picture from here, the shape is linear shape, and what will be the angle between the 2 bonds? The angle between the 2 bonds is 180 degree. Okay, so this is how this formula is useful in predicting what is the shape, what is the bond angle. Bond angle is angle between 2 bonds, so it is 180 degree, shape is linear. Fine, and one another thing I am telling you, hybridization is sp hybridization. Done. Let us move on to the second molecule now, which is BF3. Fine. So obviously B will be the central atom. It is only 1. So boron is 2, 3. So we write half. Number of valence electrons of central atom, we have 3. Number of atoms attached by single bond, we have 3. There is no charge. That's it. Now if this number, steric number, comes out to be 3, the hybridization will be sp2. We start from sp, increase 1, it becomes sp2. And you know what the shape will be? Put boron in the center and 3 fluorines like this. Okay, now don't you think they are in the form of a triangle? So this shape is known as trigonal planar. Okay, and if you measure the angle between the two, the angle between all the bonds will be 120 degrees. This you have to remember, that the shape is trigonal planar, angle is 120 degrees. Done? Now let us move to another molecule, which is methane, CH4. So half carbon is 2, 4. So 4 plus 4 plus 0 minus 0 is equal to 4. Stop here. If steric number is 4, increase the hybridization by 1 more. So it is sp3. Okay, now if the 4 bonds are there, they have to be kept in such a way that they are maximum far away from each other. And this shape, okay, I'll tell you, you might be thinking, ma'am, why are you not keeping them at this angle? Why are you not keeping them at 90-degree angle? Because if the 2 bonds are at a 90-degree angle, they'll repel each other. We want minimum repulsion. So the 2D thing is not possible here. Now just imagine a fan. A fan is something like this, right? This is the stick and there are 3 wings. Now I'm asking you to bend the 3 wings of fan a little. So when you bend the wings of fan a little, don't you think they become like this? Okay, now this kind of a shape with the stick of the fan and 3 wings bent in downward direction, this shape is known as tetrahedral. Again, you need to know the name of the shape. And when this is tetrahedral, these all will be there at an angle of 109 degree 28 minutes, which is also known as 109.5 degree. So 28 minutes, 30 minutes is like 0.5 degree. So we simply say it is 109 degree 28 minutes or 109.5 degree. Fine. So this is how I could have told, like I am simply telling you the shape of methane CH4. Okay, let me complicate the examples. The next example I am giving you is for ammonia. This is the 4th one, I think, ammonia. Let's start carefully. Nitrogen is 2,5, half. Number of valence electrons of nitrogen, 5, plus number of atoms attached by single bond, 3. Answer comes out to be 4. Now the problem rises. Look at this. There are only 3 hydrogens. That means out of 4, only 3 will be the bond pairs. So 4 minus 3, that means 1 pair of electron has to be the lone pair of electron. Okay. Now see, as soon as I said 4, that means hybridization will be sp3 only. And if hybridization is sp3, you should have written like this. Because I told you sp3 means it's a kind of tetrahedral. Now the question is, ma'am, there are only 3 bond pairs. So put 1, 1, 1. Done? Now this is one lone pair. So let me remove this line and let me put this lone pair like this. Okay. Now what should be the expected bond angle? It should be 109 degree 28 minutes because in tetrahedral the bond angle is 109 degree 28 minutes. Am I right? Now, you remember I gave you one example that this lone pair is like more free. It needs more space. When this lone pair needs more space, it will try to expand. And when this expands, it will force this NH bond to come closer. It will force this. So this will also repel and it will force these bonds to come more closer to each other. So obviously earlier the bond angle was 109. When you are forcing them to come close to each other, now the bond angle is lesser than 109 and it is 107 degrees. This value you have to remember. Fine. Now let us talk about the shape. Okay, let me stand here and take a picture. Let us consider the lone pair as a ghost. It's a bhoot. Bhoot, you know, right? If there is a bhoot standing and I am taking a selfie, obviously only my photo will come, bhoot's photo or ghost photo will not come. So if you take a picture, click from here, you will not be able to see this, right? You will just be able to see this nitrogen and 3 hydrogens, right? Don't you think this shape is kind of pyramid? Yes, I'm talking about the same Egypt's pyramid. So this shape is known as pyramidal. Okay, so the shape of ammonia molecule is pyramidal, hybridization is sp3, bond angle is 107. Done? Let us move to the next question. Now the question is water. First of all, you have to choose the central atom. Now it's not that hydrogen is written here, so you will write hydrogen as central atom. No, hydrogen is very small. So we'll choose oxygen as central atom. Oxygen is 2,6. Half number of valence electrons 6 plus number of atoms attached by single bond 2, which is 4. As soon as I write 4, I'll write sp3. But the problem is out of 4, only 2 bonds are to be prepared. So bond pair will be 2, lone pair will be 2. Done? Let us first write, if it is sp3, what should be the shape? It should be something like this. Tetrahedral, but only 2 hydrogens we have. That means this and this I have to remove and I have to make them as lone pairs. Done? Now the situation is even more clear. These lone pairs repel each other. This lone pair repels the bond pair. This lone pair repels the bond pair. That means these two bond pair of electrons will be forced to come even more close to each other. In case of ammonia, the repulsion was just because of one lone pair. In case of water, the repulsion is because of 2 lone pairs. So the decrease in angle will be even more. So earlier in methane, the bond angle was 109 degree 28 minutes. In ammonia, it was 107, and here in water, it's 104.5 degree, which is another important value that you have to remember. Okay. Now what will be the shape of water? You won't be able to see the lone pairs. Take a picture. So if I'm taking a picture, I will just be able to see this kind of V-shaped, right? So this shape is known as bent shape or V-shaped, or some books call it as bent V-shape. Done? So this was all about the bond angle, the shape of water molecule. Now let us complicate the question a little more. And now I will be introducing one another rule which is not at all mentioned in NCERT but is like really helpful. And the rule talks about, okay, first I will do simple question. PCl 5. So phosphorus is 285 and we'll write half. Number of valence electrons 5. Number of atoms attached by single bond 5. So it comes out as 5. Now 5 means it should be sp3d. Add one more. After P we get D. How these are coming, I'll tell you later on in another video. Now out of 5, how many bond pairs are there? 5. So how many lone pairs are there? We have lone pair equal to 0. Okay. Now if the number is 5, you will be placing them in another 3-dimensional way. You will place P in the center, 1 Cl, 1 Cl, 1 Cl. Okay, this is a triangle, so I'll call it as trigonal. Now, I will place 1 Cl on the top. On the top I am placing. So, and 1 Cl at the bottom. Understood? Now, forget this Cl, just imagine, isn't it a pyramid being formed? Right? Now, forget this thing and just make a pyramid there. So, isn't it a pyramid being formed? So this pyramid is formed on the triangular surface and there are 2 such pyramids, so we call it as trigonal bipyramidal. So the shape is known as TBP, trigonal bipyramidal shape. Understood? So this was all about PCl5. Now let me talk about the rule that you are asking me, and the rule is known as Bent's rule. This is not given in NCERT. I am just explaining it to you because this is really helpful. What does this Bent's rule tell us? It says that in the case of TBP geometry, only in TBP geometry, so these 3 bonds which are lying on the, you can say, vertices of equilateral triangle, so these 3 bonds are known as equatorial bonds. This I forgot to mention earlier. So now I am telling you these are equatorial bonds. And the 2 bonds, which is one above and one below, these are actually longer bonds. Why they are longer? That too also I will explain you in a separate video. So these bonds are known as axial bonds. So axial bonds are the longer ones, equatorial bonds are the shorter ones. Understood? Now see what I am trying to say. According to Bent's rule, so this has got nothing to do with Bent's rule, this is normal explanation which I forgot. So this is, these 3 are equatorial and these 2 are axial bonds. Okay. Now Bent's rule says that if there is a lone pair, the lone pair will only go to equatorial position. Lone pair will never be kept at axial positions. It will be always going to any of the 3 equatorial positions. All these 3 equatorial positions are same. And instead of lone pair, if you have, let's say, electronegative atom, it goes to axial position. Okay, I will be making another video separately for Benz's rule. Why this is happening, I'll explain you there. But as a shortcut, you have to remember that the lone pair goes to equatorial position and the electronegative atom goes to axial positions. Okay, now let me use this Benz's rule to do a few more questions. Let us talk about another molecule which is, let us say, Sf4. Fine. So sulfur is central atom, 2H6. So we have half 6 plus 4, which is 10 by 2, which is 5. 5 means it is sp3d. So it should be this, right? Now, but the problem is how many bond pairs and how many lone pairs? Bond pairs are just 4, lone pair is just 1. Okay. Now the question is, where should we keep the lone pair? If I would not have told you the lone pair, the Benz's rule, you would have kept the lone pair either here, 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 or here, anywhere you can keep. But now I am telling you, according to Benz's rule, the lone pair should be kept only and only on equatorial position. Either you keep here, here, or here. Now this is much easier for me to keep it on this position. Okay, fine, and this is Sf4. Now see, this is lone pair, this is bond pair. It will repel it, it will repel it. There will be repulsions and it will be something like this. And this is the lone pair. Okay, now this is the shape of the molecule. Now what should be the name given to this particular shape? Let us imagine, have you seen a seesaw? You must have gone to park or somewhere where you would have seen seesaw. It's simply like a seat is there and one child sitting here, or maybe you sitting here, your bandi sitting here, right? Or you sitting here, your banda sitting here. So just consider this is S, F, 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 and this is the lone pair. I just tilted it like this. So this shape of Sf4 is known as seesaw shape. Done? So I hope this thing is also clear. Now let us move on to the next example, which is ClF3. Let's try to do this. Half. Chlorine is 7, 3 fluorines. Again 10 by 2, 5. 5 means sp3d. sp3d means something like this. Now the question is, how many bond pairs and how many lone pairs? 3 bond pairs are there and 2 lone pairs are there. Understood? Remember Benz's rule. Lone pair goes to only and only equatorial position. And I have to go through 2 equatorial positions, so I'll better write it one here and one here. Understood? One Cl in the center, F, F, F. Done? Now this and this lone pair repel each other. This repel, this repel. So don't you think it's a kind of T-shaped molecule? Can't you see this T thing? This is T-shaped molecule. Done? So this was about ClF3. Let me give you another example, and this is SF6. Let's go for this example. Half. Sulfur is 6, 6 fluorines, so 6. Oops, this is a new situation. I never discussed this new situation with you. So here the steric number is 6. That means hybridization will be increased by 1 more, which is sp3d2. Done? Now, this shape is said to be, so this you can see a kind of square is there, and this is F, this one F is there. Okay? Remember, the shape is also known as square bipyramidal, and sometimes we also call this shape as octahedral shape. Octa means 8, hedral means sides. So 8 faces are there, so the shape is octahedral. So you can see 1, 2, 3, 4. a square is there and a pyramid is there. Okay, so 1, 2, 3, 4, four-sided pyramid and four-sided pyramid downwards. So 8 faces are there. It is said to be octahedral or square bipyramid. Now one thing which I have to tell you, the use I will be doing in the next video, but here you have to remember that in the case of square bipyramidal, these are not known as equatorial, these are not known as axial. They are of the same length of the same type. Okay, so we cannot use Benz's rule in this particular molecule where the steric number is 6. Fine. So guys, this was all about the Vsepr theory. If you go through the traditional method, it will be kind of mugging up thing. But if you remember this formula and a few things which I told you, you will be able to do almost every example that comes in place. Okay. Do remember to watch my next video where I will be solving 40 questions based upon the same concept, and out of those 40 questions, at least 2 or 3 of them will be there in your final exams for sure. Okay, so make sure you do watch the video. Thank you very much. Bye-bye.